All right, so first unit, okay, is kinematics. Kinematics is the study of the movement of objects. Just the movement, okay, not why the movement is happening, not the forces that are causing it, just the movement itself, right? So we're going to look at the motion of objects and systems described in terms of displacement, time, and velocity. Displacement, vector or scalar quantity? Vector. Okay? Displacement has magnitude as well as direction. Okay, like 25 meters north, okay, or 100 kilometers southwest or something like that. Okay, it has a magnitude as well as the direction. Okay, velocity is how fast you are going and in what direction. Right, so it gives you essentially your speed with a direction, because speed is a scalar quantity. Right, that's why you get a speeding ticket and not a velocitying ticket. Okay, the police are never going to give you a velocitying ticket. Okay, because if you're going the wrong way and speeding, that's like a whole separate thing. Okay, that's like 2 tickets, and you don't want that. All right, so speeding ticket means you are going too fast. They don't care which way you were going. All right, and then distance is the other scalar quantity. Distance just says how far you've gone. All right, so we'll be talking about that. Okay, so we'll be comparing and contrasting scalar and vector quantities. Okay, scalar quantities, like we said, they just have magnitude. Right, so they just have a measured value with units. Okay, whereas vector quantities have a measured value with units as well as whatever direction they're going. Okay, and then lastly here, defining velocity as a change in position during a time interval. So back in Science 10, okay, you were taught this formula. V equals d over t. Okay, so velocity equals displacement divided by time. Well, displacement is the change in position, right? So that means the final position minus the initial position divided by time, right? All stuff that you did in Science 10. Okay? In Science 10, you also learned this formula. V equals d over t. No, it's not deja vu. Okay? Why are those formulas different? Right, one of them is vector, one of them is scalar. Okay, this V is velocity. This D is displacement. Velocity is displacement divided by time. This V is speed. Does not have the arrow over top denoting it's not a vector quantity. The arrow says this has a direction. Okay, so this is speed equals distance divided by time. Okay, is time vector or scalar? The tough one. Can time go sideways? No. Okay, time is not a vector quantity. Time is scalar. Okay, as far as our experience goes, time only goes one direction. Okay, and that is it rolls along. Okay, there's lots of theoretical physics out there that says time is, just like anything else. It's a dimension just like anything else, and there are different ways to go in it, but we can't experience it that way yet. So for us, time is scalar. Okay. Now, in North America, we have a major problem with the way we describe distance. Okay, and the reason for that is how we get around. Okay, we get from place to place usually by driving there, right? And so we have this idea that when someone wants to know how far somewhere is away, they want to know how long it takes to get there, right? Because if I asked you right now, how far is it to Edmonton? Probably a bunch of you are thinking it's about 3 hours. Agreed? Because that's how we think in North America, right? Someone says, how far is it to this place? And we tell them how long it takes to get there. Okay, did we actually tell them how far it was? No, we didn't. And here's the real problem with that. How far away it is a fixed value that won't change. Can it take them different amounts of time to get there? Especially in Alberta, right? Okay, like in the summertime, it might only take a few minutes, but in the wintertime, it could take an hour, right? Depending on the road conditions. Time is dependent on other things. So we should never tell somebody how far away something is by telling them how long it takes to get there, because that value can change, right? But Edmonton is 320 kilometers from here. It was 320 kilometers from here 100 years ago. Well, it was much smaller then, but it was still 320 kilometers from here. Okay, that's not going to change. Okay? But how long it takes to get there can change. It's dependent on other things. Right? So that's one of the things we have to get our head around, because sometimes a question will say, you know, here's a bunch of information. How far did this thing go? I want something in meters or kilometers, not something in seconds or hours as an answer for a question like that. Okay, so we have to kind of wrap our heads around thinking proper physics-wise as opposed to social convention-wise. All right, so the way we typically describe things doesn't really help in a like roadless or trackless environment. Okay, if you're, you know, let's say hiking in the wilderness, and you come upon a person and you say, hey, you know, I'm trying to get to this campground, how far is it? And they tell you, oh, it's like 20 minutes from here. How useful is that? Especially if there's no trail to follow, right? It's not all that useful. They didn't tell you which way it is. They told you how long it took them to get there. Okay, these are not necessarily values that are going to be the same for you. Okay, a friend and I had this experience one time when we were backpacking in Kootenay National Park. Okay, we'd been hiking all day in 30-degree weather. We were out of water. Okay, and we were actually following a trail, and we still weren't at the campground we thought we should have been at. And then this guy comes bebopping up the trail, and like this was a steep part of the trail, and he was like jogging / running with a gigantic pack on in like full camo. We didn't really think about that at the time, but he just came bebopping up the trail, and we're like, hey, did you just come from Tumbling Falls Campground? And he's like, oh yeah, it's just 15 minutes down the trail. And we're like, sweet, we're almost there, because we're out of water and we're hungry and we're tired. We got to the camp 45 minutes later. We were cursing this guy for a half hour. Okay, it's like that. We used a lot of expletives, but you know, we weren't very happy with this guy, because we figured we should be there already, because he told us 15 minutes, and he was going uphill and we were going downhill. Now, when we finally got some food in us and started thinking straight, we're like, okay, guy was wearing like army fatigues, carrying an army pack that was gigantic. Guy was probably a Navy SEAL, like he was probably out for an afternoon jog, okay, you know, and he was in incredible shape. Meanwhile, you know, we're just two teachers on summer vacation. My buddy's like 5'4", his legs are only about this long. Okay, you know, he was slowing me down totally. You should always hike with someone slower than you. Why? Bears, yeah, always hike with somebody slower than you. That way the bear goes after them instead of you. Yeah. I told him that. He's like, yeah, but he was a nationally ranked wrestler. He said, I know where you keep your knees. You're not going anywhere. So, yeah. All right. So obviously telling somebody how long it takes to get somewhere is not very useful. Okay. Unless there's, you know, an absolutely defined route with a defined speed that's always going to be the same, then maybe. Right. But we want to do a kind of a better job of that. Okay. So if we say to somebody, Calgary's 40 kilometers from here, we're giving them a scalar description of the distance to Calgary. We have to assume then that they can get on the road and follow the signs and get to Calgary. Pretty safe assumption, right? If the person lands in a helicopter and asks you where Calgary is, would you give them the same answer? Because they're probably not going to follow the road if they have a helicopter. Okay, they would, you know, they would want a heading, in which case you would give them a vector description. It's this far and in this direction, and then they could head that way because they can go in a straight line. Okay, so a more descriptive description of where Calgary would be giving them a vector description. Okay, and that would be that it's 40 kilometers away on a vector of 13 degrees west of north. Okay, is 40 kilometers more or less accurate than 40 kilometers at 13 degrees west of north? Is there a difference in accuracy? One seems like it should be more accurate, right? Because it gives more information, okay? But it's just giving you more information. That information isn't necessarily more accurate, okay? And this is another thing that we confuse typically in North American society is 40 kilometers at 13 degrees west of north is the same accuracy as 40 kilometers. How accurate, at 13 degrees, not kilometers. Okay, how accurately did I measure both of them? They're accurate to plus or minus 1 kilometer, right? 40 kilometers means this thing is somewhere between 39 and 41 kilometers. Right? There's no decimal there, right? Okay. Had I measured one of them and said it was 40.1 kilometers, okay, that is more accurate than that because it's measured to the nearest 100 meters, where this one is measured to the nearest kilometer. Right? So these are equally accurate. This one's more descriptive. Okay? This, the 40.1, is more accurate than 40. Okay? So accuracy is based on how you measure something, not how much information you give. Right? So a vector quantity could be less accurate than a scalar quantity depending on how it was measured. Okay? So vector quantities are not always more accurate. Okay. So let's say we have this situation here. Okay, I need to go from my house to Walmart. Okay, since I don't live right behind Walmart, I can't walk in a straight line there. I have to follow roads and make turns and go over bridges and whatever else. Okay, so I follow the road. Okay, I go over the bridge and eventually I end up at Walmart. Right? Let's say that that black line there represents a total distance of 4 kilometers. Okay. Have I gone 4 kilometers in a straight line? No, right? We're all familiar with the saying, the shortest route between 2 points is a straight line. So obviously the purple line on that graph is not 4 kilometers long. Okay, it's much shorter. So this black line, which is 4 kilometers long, is the distance that I travel from my house to Walmart. Okay, it's how far I went. It's a scalar quantity. It can't give direction because I went a whole bunch of directions along that path. Sometimes I went a little bit west, and sometimes I went straight north, and sometimes I went northwest, and whatever. Okay, there were a whole bunch of different directions, but my total distance traveled was 4 kilometers. Okay, the purple line, okay, represents our displacement, and it's probably going to be less than that. Everyone with me so far? Okay, so the purple line is going to be 2.8 kilometers on a vector of 38 degrees north of west. Okay, so it has kind of a right angle triangle that looks like this. This angle here is 38 degrees and it's 2.8 kilometers long. All right, so let's say in walking to Walmart along the black path took me a half an hour. How fast was I going? I walked 4 kilometers in a half an hour. How fast was I going? 8 kilometers an hour. Okay, here's how we figure that out. How fast? Is that velocity or speed? Which one's scalar? Velocity or speed? Speed. Okay, speed's the scalar one. All right, so since I didn't ask how fast and in what direction, I just asked how fast, I'm looking for speed. Okay, speed is distance divided by time. And we know that the distance was 4 kilometers. And the time was a half an hour. Okay, 4 divided by 0.5 is 8. Kind of makes sense, right? If I'd have kept walking, I'd have walked 8 kilometers in an hour. Okay, I walked 4 kilometers in a half an hour, I'd have walked 8 kilometers in an hour. Everyone okay with that idea? All right, so just figured out my speed for this part of the trip, right? If I want to find my velocity for this part of the trip, then I'm going to use the other formula. I'll use this one. Velocity equals displacement divided by time. Now, the question told us that my displacement is 2.8 kilometers at 38 degrees north of west. Right? So I'm going to go 2.8 kilometers at 38 degrees north of west and divide that by half an hour. Right? I'm just going displacement divided by time. Right? Since there's no direction on the bottom, does my direction stay the same? Yeah, it has to. I can't have a displacement 38 degrees north of west by traveling at a velocity of whatever kilometers per hour south. Agreed? Like you can't end up northwest by going south. It just doesn't work that way. So what I'm going to end up with here is that my overall velocity is 5.6 kilometers per hour at 38 degrees north of west. Okay? Your velocity and your displacement always have the same vector, okay? Because they're along the same line. Questions so far on that? All right. I get to the door of Walmart and realize I don't have my wallet. Okay? I'm not a person who just walks around and looks at stuff, so I turn around and I walk straight back home along exactly the same route. So surprising, surprise, surprise. It takes me exactly a half an hour to get back home. Right? What's my overall distance traveled? Awesome. 8 kilometers. I walked to Walmart 4, I walked back home, it's another 4. I took exactly the same path. So I walked a total distance of 8 kilometers. What's my total displacement when I get back home? 0. Okay? Remember that displacement from Science 10 is how far and in what direction you have gone, or your total change in position. My starting position was home. My ending position was home. I haven't changed my position. Therefore, I have not displaced myself from where I started. So my total displacement is 0 for the whole trip. And what's my average velocity over the whole trip? 0, right? Velocity is displacement over time. And I just said my displacement when I go back home is 0. Okay? 0 divided by anything is 0. Ringing a bell from Science 10. If you took my Science 10 class, that just seemed really familiar because it's exactly the same example I used. Okay. All right. Now, let's say I'm walking along this map. Okay, the little hashed marked lines are trails. So let's say I'm standing right here at Seldom Inn Campground, and I want to go to here, which is Snake Indian Falls Campground. There's a sign at Seldom Inn Campground that says Snake Indian Falls Campground, 28 kilometers. What is that sign giving me? It's giving me a distance. Okay, what does that sign assume I'm going to do? Follow the trail. Okay, this is kind of some of the things we need to understand about how stuff works. That sign doesn't say Snake Indian Campground or Snake Indian Falls Campground, 7 hours. Okay, because how long it takes me to get there is dependent on a lot of things. Conditions of the trail, how good a shape I'm in, whether I'm walking or riding a horse. Okay, it all makes a big difference on how fast I'm going to get there. So it gives me the one thing that isn't going to change, how far it is along the trail. Right? This sign doesn't say Snake Indian Falls Campground, 20.68 kilometers at 42 degrees north of west. Okay, why would it not give me that? Do I want to walk that way? I mean, there's all manner of disaster along that path. Okay, there's like canyons and cliffs and glaciers and rivers, and yeah, I probably can't go that way, right? But if I follow the trail, I'm much more likely to get there, right? So there's a time and a place for giving somebody a scalar description. Okay, that's a time and place for a scalar description because it makes the assumption I'll follow the trail, right? There's a time and a place for a vector description. If I'm sailing across the ocean, okay, a vector description is more appropriate. There aren't roads to follow. Okay, if you want to go from here to there in the ocean, it's this heading and it's this far. Okay, so go this far along this heading and you'll be there. Right, so you always have to kind of pick one that fits the situation. All right, so this should be a review here from Science 10, just kind of definitions here. Speed is a measure of the distance traveled in a certain time interval. So its units are like meters per second or kilometers per hour or things like that. Same with velocity. Velocity is your change in position over time. So it's got meters per second or kilometers per hour along with a direction. Okay, and so these are just the answers to what we did before, the 8 kilometers per hour, and the 5.6 at 38 degrees. Okay, so it's the calculations we did from that previous diagram. Okay, so more terminology here just as a review. Okay, a scalar quantity is any measured quantity that has only a value, okay, a measured value usually with units, right? So scalar quantities, speed, distance, time, energy, work, mass, okay, things like that. Your mass is how much of you there is, okay, so that's just a scalar quantity, right? Distance is a scalar quantity that measures how far an object has traveled, right? The odometer in your car, the one that tells you how many miles or kilometers are on your car, does that measure distance or displacement? Exactly, it measures distance. Why wouldn't it measure displacement? What would it read every time you came home? No, it would read how far your house is from the dealership you bought it at. Still too early in the morning for that one. I get everybody with that one. Everyone says 0. Okay, so yeah, it would always read the same number essentially. It'd be great if you were trying to sell it, right? Because then you could say it only has like 4 kilometers on it. Okay, that'd be awesome. Even it could have 25,000 or it could have 250,000. Well, usually they're brought by truck. Only if the wheels spin. You have to drive it. You have to actually drive the truck. The wheels have to turn for the miles to go on the odometer. Yeah. Like, and back in the day, you could when they were analog, they were like a clicker. You could take their face off, and people would turn them back, okay, and say that there was less if they were really dishonest. So yeah, now with the digital ones, that's a lot more involved process to scam people that way. Okay, but yeah, you're right. It would read. Yeah, the wheels actually have to spin for it to record. If you've ever seen Ferris Bueller's Day Off, they tried to make the Ferrari's odometer go back by putting it in reverse and putting the wheels off the ground. That doesn't work either. Okay, now, your odometer doesn't go back if you drive in reverse. In fact, it still goes forward. All right. So vector quantities, any measured quantity that has both value and direction. So 40 kilometers forward, 3.2 kilometers at 18 degrees west of south, 400 newtons west. Okay, it's always going to be something with a direction on it. So displacement's a vector quantity that measures how far and in what direction an object has traveled from its starting position. We could also write kind of more simply, it's the change in position, delta P. Okay, that's final position minus initial position is another way to calculate displacement. Okay, and then we said velocity is a vector quantity that measures the displacement of an object during a set time interval. So how fast are you changing your position? Okay, questions there? Hopefully that's all fairly familiar from Science 10 for you. All right, so we're going to go over a few examples here just to kind of refresh our memory and make sure we still know how to do this stuff. Okay, so let's have a look at this one. So I have this person who is standing 1.5 meters to the right of this Inukshuk. Okay, so this is where they're standing right here. Okay, then they're going to move so that they are 3.5 meters to the left of the Inukshuk. Okay, determine the traveler's displacement. All right, well, we just said a minute ago that displacement is your change in position. That means final position minus initial position. Now, their initial position is 1.5 meters right. Their final position is 3.5 meters left. Left and right are opposites. Mathematically, that means one's positive, one's negative. Okay, so we use a lot of positives and negatives when we're talking about direction. All right, so their final position is negative 3.5 meters. Okay, and their initial position is positive 1.5 meters. Okay, so negative 3.5 minus positive 1.5 should be negative 4.5 meters. Now, do I want to leave it as a negative? What did the question tell me? In terms of direction, the question said left and right. So I can't leave it as a negative because that's not the directions the question gave. Negative 4.5 meters actually means 4.5 meters. Which way? Which one did I make negative? Left. Okay, so that's how we can calculate displacement. Final position minus initial position. You did that on graphs, on position versus time graphs all the time in Science 10. Okay. All right, questions there? Pretty okay with that one? All right, I want you guys to try those three. Okay, I'll make them a little bigger so you can see them. All right, so just try 1 and 2 for now. Okay. See if you can figure them out. I'll give you a couple minutes. All right, so for our first question here, these sprinting drills include running 40 meters north, that's what the N stands for, walking 20 meters north, and then sprinting 100 meters north. Okay, what's the sprinter's displacement from the initial position? Well, they're all in the same direction, so all I have to do is add them all together. All right, so we're going to be looking at 160 meters north. Okay, it did ask for displacement, so I do have to put the direction on there. Okay, had the question just asked how far did they go, then it would just be 160 meters. No direction because it doesn't matter. All right, how many people have done number 2? Okay, let's have a look at that one then. All right, so to perform a give and go, a basketball player fakes out the defense by moving 0.75 meters to the right and then 3.5 meters to the left. What's the player's displacement from their starting position? All right, so here's where they start. They move 0.75 meters this way, and then from here, they go 3.5 meters this way. All right, so how far did what's their displacement on this one? Okay, 2.75 meters. Yeah. Okay, all I got to do is subtract my 0.75 here. Right. So I'm going to go that I went 0.75 meters to the right, 3.5 meters to the left. Okay, and I'm going to have my 2.75 meters to the left. All right. How many people have done number 3? Okay. I'm going to give you a couple more minutes on number 3, and then we'll go through it together. So while building a wall, a bricklayer sweeps cement back and forth. She swings her hand back and forth a distance of 1.7 meters 4 times. Calculate the distance and the displacement her hands travel during that time. All right, so she starts here and goes 1.7 meters that way, then 1.7 meters back, then 1.7 meters this way, and then 1.7 meters back. What's her displacement? 0. She ends up back where she started. Right? But her total distance traveled is going to be 4 times 1.70 meters. Okay? Because distance doesn't care whether you go back and forth and end up back where you started. It just cares how far you went. Okay? So that's why it's 6.8 meters for distance and 0 meters, okay, for the displacement. All right, questions on any of those? All right. Okay, I would like you guys to write down some answers for the following questions. Okay, I'd like you to do question number 4 and question number 5 for right now. Okay, just those 2 for right now. All right, so on number 4, okay, we're being essentially demonstrated the importance of giving vectors in a question in order to place things in the right position. Okay, so we're told that Chad is 2 meters left of Dolores. They don't tell us where Dolores is. They just tell us that Chad is 2 meters left of her. So I'm just going to write a D for where Dolores is. Okay, and then I'm going to put Chad 2 meters to the left of her. So I'm just going to say here. Okay, so 2.0 meters. Ed is 4.5 meters right of Chad. Well, that means that he's how far from Dolores? 2.5 meters this way. And that's Ed. Okay, Greg is 7.5 meters left of Chad. So he's like way over here. Okay, and Hannah is 1 meter right of Ed. All right, so what's the displacement of a teacher who walks from Greg to Hannah? All right, so Greg is over here. He's the furthest one on the left. So any teacher walking from Greg to Hannah is walking which way? Right. Okay, so we just add them all up here then. We got 7.5 9.5, 12, 13 meters to the right. Okay, so it's the importance of knowing being given vectors. We can locate things, okay, as long as we're told the exact positions of everything else. All right, how are we doing on number 5? How many people have done 5? Okay, I'm going to give you a couple more minutes on 5 before I do that one. All right, so for number 5, the key to number 5 is to remember that we can solve for displacement using the change in position. That's final position minus initial position. So all we have to do is a little bit of algebra here in order to isolate what our final position is for this question. We know the displacement is 50 kilometers west, okay, and we know the initial position is 5 kilometers east. Okay, so I'm going to make east positive and west negative in this question just so I have that, right? I want to get my final position by itself. So what do I have to do to initial position? If I want to move something, I do the opposite. So right now I'm subtracting, so I want to add. All right, so I'm going to add initial position to both sides. Okay, so it'll cancel on this side, and it'll end up over here. So initial position plus the change in position should give me my final position. All right, so that's going to mean then positive 5 plus negative 50. Okay, because we said west would be negative. All right, so that means that our initial position then was, what's 5 plus negative 50? Negative 45 meters, which is 45 meters east. Okay, I must have started 45 meters east of whatever the reference point is if I ended up, okay, 5 kilometers east after traveling 50 kilometers west. Okay. All right. Everybody okay with that one? Oh, sorry, I got that backwards. I got it backwards. Sorry. West, not east. East was positive. Sorry. I haven't had my full cup of coffee yet, so I'm not totally alert. Okay, questions there? Besides, Coder, you screwed up on first day. A terrible first impression. All right, so we'll leave it at that for today. Okay, make sure that for tomorrow you have access to the notes package and the worksheet book for Unit 1 at the very least. Okay, again, if you're deciding to print that, print it in black and white. Okay, don't spend a bunch of money on printing ink. Okay.